Algebra textbook analysis slides. It's a presentation that'll be given this Thursday at the Common Core State Standards Professional Development Day. So here's what I intend to do. Show a PowerPoint and say, all right, this section is going to be about analyzing your textbook, your algebra textbook, from the Common Core perspective. You also want to call this what's wrong with my textbook. I don't know about you, but I'm not a big textbook fan. Usually put you in a straitjacket, and that is the antithesis of the Common Core. What flexibility, freedom, multiple answers, sources of error, things like that. The expert at this is Mr. Dan Meyer. He gave a talk at the TED conference recently, a year or two ago, and it really encapsulates what we're talking about. So go to this and watch the video if you're interested and see what he says. I actually watched the video dozens of times, and I find it fascinating every time. So at this point, I would actually show the video for the class. After the video, I would say, so here's a recent email I got from Dan Myers. What he talks about is the ladder of abstraction. And we go up and down this ladder as teachers, as experts, many, many times a day without giving it a second thought. And we need to understand that our students are not on the same plane as us. A great example of that, where we just say, oh, we've got a problem here, and now we start out at a certain level, would be the any card problem. If you did a card problem earlier today, ask your students, how many cards are in a deck of cards? How many suits are there? What are the name of all the cards? Some of them will know, they play cards with grandma, but many of them don't have the faintest idea what a deck of cards even is. They might have seen it in a TV show or in a movie at some point. They've never actually looked at one, or if they've played one, like my younger children have, they don't know how many cards there are, or what the names are, or what the name of the suits are. There's, 2 red suits and 2 black suits, and that's about all they know. So when you are working with your students, you need to consider what rung they are in the ladder of abstraction. So this one is pretty close to the end, and it's pulled from a textbook. It's another one textbook. And out of curiosity, I wonder if you know what unit this should be in. Hopefully your teachers realize this is a classic Pythagorean theorem problem for distance formula. And if you look at this problem, it's a good little problem. We look at it, that's a nice little problem, but truly, you can do better. This would be something they might understand. Here's a satellite shot. Where are the cities? Where do you think they are? Right? What is this? What is all this green? What are all these little cracks? So now you have students looking at a picture, which is kind of an interesting picture. Maybe they've never seen a satellite shot of the Earth before, and you tell them that's what this is, and they start to think, oh, so that's what it is. And this is a much lower rung of the ladder. Is it the bottom rung? Maybe, maybe not. Some of your students may not have any idea. Maybe they've looked at Google Earth and they're with you on this. But it's a good place to start. It's a heck of a lot lower than where the previous picture was. So now you've moved up a rung. We have represented real world things with shapes, lines, numbers, names. And now you can say, even go back and forth between the previous picture and this one. Say, okay, so where was the city? Well, here is Bend. Here's another city. Here's another city with what may or may not be an airstrip out there. That's what it looks like. Redmond and Sisters and Bend. I believe this is in Washington State area, but I'm honestly not sure. And we've cleared away all the other stuff so that we can look at it and say, oh, there's cities. There's a lot more going on here. There's rivers and mountains, and this looks like a national park off to the left. But at least now the kids have a second, have an idea of where we're going with this. This is a great place to start, to move to. We're still not even close. We can say, listen, let's get rid of all this stuff. We've got 3 cities. Now we actually introduce the question, where should we put a cell phone tower? They say, well, right in the middle. So, well, where's the middle? Well, in that general area. Well, can we be more exact than that? Can't just go out and somewhere and pray that we got it right. How do we get it right? And let the kids come to understanding that numbers can't just exist in space. You have to give them some organization. So hopefully they figure out, you know what, why don't we put it on a grid? And now I can actually count. Well, Sisters and Redmond are 1, 2, 3, 4, 5, 6, 7. There are 8 apart. And Redmond and Bend aren't on the Same line. So how do we figure out how Redmond and Bend far apart they are, how Sisters and Bend are, and let's pick a point. How about here? Or, let's label A, B, C, D, E, F, and say, which one do you think is the center, the best spot, and why do you think that? And now you're getting an argument going. You're getting discussions. You're getting kids thinking, and you've built up to it, and they understand why the grid is there. This is what we're looking. This is what we're looking for. Is it worth your time? Common Core says absolutely. And this is how math is taught in other countries. Think about it. Look at it. Try it. Are you getting anywhere? No. Why not? Have you talked to a friend? Bounce some questions off of me. I'll just bounce questions right back and help you move in the right direction with questions. Maybe I put a hint in an envelope and I hide it off to the side. Maybe you've already seen the Pythagorean theorem. Maybe this is an introduction to the Pythagorean theorem, saying, well, if we're on a grid, I can show you how to find the distance. Maybe you need some manipulatives. Maybe you need string with circles. Who knows? Maybe you need to print this out and let the kids play with it. These are things to try to get them thinking, to get them actively participating. Here's a great problem from a textbook. But, I'll come back to the but. This is a geometry textbook, and you have a cow tied by a rope that's 25 meters long, and the dimensions aren't shown on here, but they exist. There's a barn and a garden, and the garden has a fence around it. So how much grazing area does the cow have? Now, it's a great problem. It's real, it's authentic, it's a good question. If the cow doesn't have enough grazing area, maybe it'll die. Ask that question. Why do you care? Should we care? Anybody here work on a farm? Did you ever see what the cows do to the grass? Yeah, they cut it down to nothing. This cow's going to starve to death if we don't give it enough grass. Something like that. Let them figure out how to make it more abstract, how to make it more mathematical. What should they do? Well, here's the problem I have with this. This is just a throwaway problem. It's like number 17 in a textbook of 40 problems for homework. And it's a great problem. It should be, here's a problem to try. It's an area in geometry on sectors of circles. And if you know pi r squared is the area of a circle, you can do this problem. You have to actually think about it a little bit and consider how you're going to do it, maybe bring a protractor and that sort of thing. But hopefully they're smart enough to realize what to do to make it more abstract. This is the classic textbook solution. You might even want to show them and then say, well, how do we figure this out? I wouldn't, but it's not a bad idea, especially for younger kids. And if you have a second problem, they can follow up on it. You can calculate the area of that light blue triangle and the purple sector and the orange sector and the yellow semicircle and the orange sector, red sector. But before you do any of this, what would you do if you had a bunch of middle schoolers? At this point, I'd let the audience try and come up with solutions. And the solution, of course, is to get some graph paper and some string. And now they've got to figure out how to scale things. And now they've got partners that are putting their fingers on the posts, and they've got to wrap the string around there and figure out what the radius of that sector of circle and orange is, things like that. So this is what they're going to do, and this is what they should look for. And they should take some time now, sit down, either with a partner or on their own, and try and find a textbook problem that they can turn into a 20 to 30 minute classroom problem. That's what this is. It was a homework problem, and I had so many questions on it. I finally said, you know what? This is a great problem. The next year I taught it. I said, let's take this problem. I put it up on the board. I said, now you guys got to solve it. What are you going to do? And they all stared at me blankly, saying, don't ask us to actually make decisions. Just give us A, B, C, D. I get my little check mark. I get my A+, and I can move on with my life. They don't want to have to think. This is a great opportunity to get them thinking. So if they don't start, I say, well, you got 30 minutes to solve it, so knock yourselves out. It's a graded assignment. I'd like to see what you guys can or can't do. I said, well, maybe I could throw it on a grid or something. Oh, that's a good idea. Does anybody have graph paper? Do you think I do? And everyone said, of course you do. Well, here it is. How are you gonna see what the rope does? Maybe you need a piece of tape. Maybe you need some string. Oh, I have string and tape too. Go ahead. And I give them 30 minutes and I circulate the room and I ask questions. I let them play with it. I let them think about it. I let them draw it. I said, do you have any colored pencils? I have some. Maybe they want to put it in color. Maybe they just want to put it in different types of cross-hatching. And there are several ways to solve this problem. Some kids just draw the full circle so everything looks yellow and they subtract out how big the garden and the barn is. Other kids just add up the squares. And then they got half square here and a half square there and they ballpark it. That answer is usually right within plus or minus 5%. Some kids don't see the red piece and oh, that's right, I forgot that. This is a chance for them to think, to play with a manipulative, to work it out as best they can. So now everybody in the room has brought an algebra book. If not, hopefully you can find somebody who has. And then you have a chance to try now. This is the actual chance for you to find a problem or two, hopefully in a unit you're using, that you can try in class in the next week or two and see if you can get the kids working on their own, thinking on their own, trying on their own. Good luck.